So let's welcome Laurie.
Thank you guys so much. And you might think that the fact that I have lots of undergrads working with me is because I'm some super professor doing some crazy cool research. I assure you that's not the case. You can see why the undergrads want to work with me from this picture here, is that I go to places with cool animals in warm tropical climates and palm trees. And you'd be surprised that undergraduates on spring break, if they're offered the opportunity to go hang out in a warm tropical climate with beaches and so on, they often say yes. So, it's not me, but hopefully I'll be able to tell you guys a little bit about what I do today. Here's the kind of roadmap of what I want to get through. Kind of wanted to start a little bit with an introduction to kind of how I got into this stuff, and then I'm going to talk to you about why it might make sense to actually study monkeys if you're interested in humans. I'm not actually a biologist or an animal behavior researcher. I consider myself a psychologist. I actually trained in psychology, and I'm really interested in humans, not monkeys. So I'm going to talk about why it would make sense to go to these tropical places and study monkeys if you really care about how people work. And then I'm going to give you 3 different test cases where I think we've learned something about the human mind by turning to monkeys. And those test cases are going to be looking at what monkeys know about number, whether they can count and do arithmetic, what monkeys know about minds, whether they're good at thinking about what others are thinking, and most recently some work we've done looking at whether monkeys know something about money. And then we'll sort of wrap up and so on. But if you have questions as you go through, definitely raise your hand and call on me so that we can stop and go through it. But I want to start with a little bit of a misnomer, because I think folks think that most of the professors here at Yale are kind of these stodgy folks who end up in lecture halls, teaching in buildings like this. But perhaps unlike some of my other colleagues, I lead a bit of a double life. Because yes, I do this. I sort of teach in these kinds of classrooms that look like this. But I also have the opportunity to head off to these gorgeous places, in part because I study these populations that don't necessarily live on college campuses. I study a bunch of different non-human primates. There's one of the non-human primates I study. His name is 39L. And he's one of these guys on our field site. But I took a little bit of a strange trajectory to get here, because this is something that until probably about 10, 15 years ago wasn't even on my radar at all. I actually grew up in a sort of big working class town in Massachusetts known as New Bedford. It's kind of about the size of New Haven or even Bridgeport. I went to a big urban public high school where nothing like the kind of stuff I'm doing now was ever taught to me. I learned a little bit of biology, I learned a little bit of science, but I didn't even know that this field existed. And it was actually through the act of going to lectures when I first started to go to college that I learned that this field existed. I was sitting in a big lecture hall, much like you guys, when I was a freshman, and I heard about the fact that this work existed, the fact that you could be a person who is interested in humans and use animals as your model to get at it. And I just found this really fascinating, and it helped that my undergrad advisor at the time threw up those pictures of the beautiful tropical spots, and I said, I am in. And somehow it stuck. So just be warned that sitting in a lecture hall like this might change the course of your life, where you end up off in tropical places hanging out with monkeys. So if you want to take off now, you can do that, but you've had your warning that this could happen. But the question I want to start with is this issue of why would you want to study monkeys if you care about humans? And I think the way to frame that is based on an intuition that I think you'll get. So imagine you're trying to learn about a human. Imagine you're trying to learn about a new person that you meet for the first time. And so I'm going to get to that by sort of switching gears and actually asking this question: why should we study monkeys to learn about humans? So imagine you're meeting a person for the first time. Let's say you go to a new high school, or those of you who are in high school, you go to a new college for the first time. You're meeting people that aren't just from New Haven or West Haven from Brantford, people from all around the world. What do you want to ask them to get to know them for the first time? This is the audience participation part. So what do you ask them?
Name.
Your name? You want to know their name? Their age, something about how old they are. Where they're from, exactly. So this is, you guys, you are not a plant. That's actually what you see. And this is fascinating, right? I can be in a group of folks here. I've given this talk all around the world with the same setup. And most of the time, people come up with this pretty quickly. It's usually in the top 2 or 3 things you want to ask somebody. Where are you from? Why do we care? Well, we care because where somebody's from actually matters for who they are right now. If you grew up in Brantford or New Haven, we think your experiences are going to be really different than if you grew up in Florida or San Francisco or Thailand. Where you're from actually tells me something that's very causally relevant for who you are right now. And I can learn a lot about you by figuring out where you came from. This is basically the logic of why we turn to studying the origins of cognition from an evolutionary perspective. The idea is, if we really want to know where humans are from, why just stop at the developmental part of just how long your life course went? Maybe we can learn something about where humans are from by considering an even broader history, one that goes way back into our evolutionary origins. And that's the idea. We're going to be trying to look at our different cognitive origins, sort of where our cognition and our thinking comes from. Because if there's a puzzle to understanding a person that you meet at camp or at a new high school, there's a bigger puzzle of trying to get at the very basis of how we think of things. So all of you right now have inside your head this sort of gob of tissue that's processing all the cool things that make up your human experience, processing things like aggravation and bright ideas and storytelling, all the kinds of things that make us us. And we still know remarkably little about how this works. What we try to do is to try to say, well, given that this is such a big project, maybe we have to get to the roots of it. Maybe we have to study its origins, both evolutionarily and also developmentally. Because one of the things my colleagues here at Yale do, and if some of you were here a few years ago, you might have seen my colleague Paul Bloom talk about this stuff. But one of the things we can do is to actually try to figure out the way the adult human mind works by going back across the developmental couch. So my colleague Paul Bloom actually studies what these super young babies over here know about the world. How do they make sense of it? He finds that they can do things like make moral decisions and so on. But the point is that you can actually see the changes over developmental time as we get older, as we get access to schooling and so on. And that can teach us something about how schooling and language and culture shapes the mind. In our lab, we do the same thing, except rather than taking a developmental approach, we take an evolutionary approach. But the idea is just the same. In an ideal world, we'd study this guy over here. And we try to see, how does he make sense to the world, given that this is a guy that probably doesn't have language or culture or any schools or anything? And how did that change over evolutionary time as we got to us with all the conveniences of modern life? There's a big problem with this approach, though, in that it's really hard to find subjects for this kind of study, because most of the guys we actually want to study are dead. They're not just dead, they've been dead for thousands, sometimes even millions of years. So we have to come up with a bit of a proxy, some sort of other way to get at this. And that is why we turn to the primates that we have here living today. Here's my student Neha, one of my former undergrads, who's now a postdoc. But she's actually turning to non-human primates to get this answer. And so for those of you who are not familiar with your primate tree, here's a kind of quick schematic to get you oriented. This is the sort of Yale-centric primate tree. And some of you are smiling, which means I think you recognize who the human I'm depicting here is. Does anybody want to call out who the George Bush, right? So we get to make fun of George Bush because he's a Yaley, and sometimes we like to do that. But George Bush is on here in part to remind us that evolution isn't a ladder with humans on top being the smartest. Remember, we're a big tree and we're all equal, at the tops. As I said, he's a Yaley, so we get to make fun of him, right? But what we try to do is to kind of compare cognition, thinking, across all the top branches of this tree. And in our own lab, we actually do this with the furthest 3 members of the primate tree. And this gives us a really wide window into the way primate cognition works. The 3 different groups of primates that we've been working with in our lab start with these guys here. These are the prosimian primates, which branched off from our own branch about 50 or 60 million years ago. We can kind of quibble about the numbers, but they're our most distant set of primate relatives. And we actually study a group of these guys down at a forest reserve in a part of Florida known as Myakka City. It's not very city-like, despite the name. These are the kinds of roads you see down in Myakka City. But if you head through the forest, you get to a reserve that's home to about 30 free-ranging lemur species. There's a couple of these ring-tailed lemur guys. They also have bamboo lemurs, these mongoose lemurs, and some of these brown lemurs, red ruff lemurs. They're all very cute. But they get to free range around a 30-acre enclosure, and we can go down there and actually study them in a relatively naturalistic habitat. So here's some of my students, Jen and Neha, who you saw before. They got Yale Fellowship money to actually travel down and work with the lemurs. Here's kind of Jen getting more up close and personal, and Neha trying to study number in the lemurs, which you'll hear about in a little bit. But this is group 1 that we study, the most distantly related branch of primates, these lemurs. We also study a second group of primates that's closer to home, both evolutionarily and kind of spatially. These guys are the branch of primates known as the New World monkeys, because unlike us, they actually evolved in the New World, so they're native to Central and South America. We actually study a group of these guys here on campus. It's a group of brown capuchin monkeys. We have 10 of these guys. They live in a big zoo enclosure, and we get to do behavioral studies with them, kind of up close and personal. So this is a resource that we have here at Yale to actually study cognition not so far from campus. So that's the New World monkeys, but as I said, we study 3 branches. So we also study this branch here. This is the branch of Old World monkeys, the monkey species that are most closely related to us. And these guys are represented by the rhesus macaque, who's the species you see here. We study a group of rhesus macaques, again in a naturalistic habitat. This is the picture that got me wanting to do this kind of work, and you can see why. This is the island of Cayo Santiago, which is right off the coast of Puerto Rico. It's gorgeous, and this is why my undergrads like to go there, because it's sort of a nice rocky beach and pretty palm trees. But it's relevant for us because it's home to 1,000 free-ranging rhesus monkeys. So again, these rhesus monkeys kind of go around and do their monkey thing, but we can go down with teams of scientists. Here's me and one of my undergrads, Jen again. We sort of get our stuff together. We could go hiking around the island, following the monkeys, watching their behavior, and then also setting up these kind of thinking tests to sort of set up some problems and see how monkeys solve them. Here's my undergrad, Brian Edwards, who's now a grad student at Northwestern, sort of asking monkeys about causality, which we might get to a little bit as well. But this is the basic approach I take, trying to compare across the tops of these different trees to see what monkeys know. Oh, and just for kicks, sometimes we present monkeys with totally crazy things that my undergrads come up with, which you'll see in a second. But you can see the monkeys are quite fascinated with these things. All right, but what I haven't told you, I've told you a little bit what I do, but I haven't told you yet is why it actually makes sense to study monkeys. Why would you want to actually turn to monkeys if what you're interested in is humans? And I think there's two distinct answers to the question, but I'm going to broaden it up and not just talk about why study monkeys, but why study animals in general. Because oftentimes, even though I focus on primates, the answers might be the same no matter what animals you actually turn to, as long as they're a non-human species. But there's two kinds of answers here. One is the answer that isn't the flavor of answer that I typically give as a psychologist. It's an answer that a biologist might give. And biologists might answer the question of, well, why would you want to study animals? They might say, well, look, animal behavior is incredibly interesting in its own right. We might just want to know how animals do what they do from the perspective of biology. And we, of course, implicitly know this. Of course, no one would spend their time going on the internet looking at things like this if what animals did wasn't sort of funny. You know, you get this sort of like lolcats version or sort of, you know, these sort of funny things. I mean, this is a sort of quip, right? We have these things on YouTube because animals do funny things, but real animal behavior is often more impressive and more intriguing. And so to do that, I'm actually going to, I just realized I need to sort of put my sound on here real fast. I'm going to show you an example of one of my favorite cases of very interesting animal behavior. See if we can get this to work. You guys hearing the bleeps there? No. All right, let's see if we can get this working. And just make sure my volume is up here.
This is this piece of the problem.
That sounded good. Well, we'll see if this works. If not, I can kind of come back to it in a sec. But. All right, well. Oh, it's this one. Hold on.
There we go.
There we go. All right. So now, as I was saying, this is my favorite example of the coolest animal behavior. And as I said, I don't pick a primate because a primate would be kind of too close to home. These guys are very, very distantly related from primates, but as you'll see, they're incredibly cool. This guy is a lyrebird, who's one of the birds that lives over in Australia and New Zealand. And you can see he has an incredibly interesting cognitive habit that he uses to recruit females when he's trying to mate with them. And I'll let the lyrebird take it away.
To persuade females to come close and admire his plumes, he sings the most complex song he can manage. And he does that by copying the songs of all the other birds he hears around him, such as the kookaburra. It's a very convincing impersonation. Even the original is fooled. He can imitate the calls of at least 20 different species. He also, in his attempt to outsing his rivals, incorporates other sounds that he hears in the forest. That was a camera shutter. And again. And now a camera with a motor drive. And that's a car alarm. And now the sounds of foresters and their chainsaws working nearby.
Okay, so you see why, yes. Always sad when the lyrebird gets more applause than me, but I understand why. Because that is just amazing. Like, how can you not find that the most fascinating thing ever? And that's not just some weird, like, video thing. That's actually what the lyrebird does. The lyrebird has to imitate all these kinds of different calls, and somehow he has a cognitive process that lets him pick up sounds and imitate them. Way better than anybody on like Saturday Night Live or any human impersonators, right? And this sort of leads to these kind of big questions, which is like, what is this lyrebird doing, right? How is he taking the sounds that are out there in the world, feeding them through his head and producing them himself, right? Why is he doing it? Why on earth did the females find this attractive that he sounds like a chainsaw? Like, that's pretty weird. How is he doing it, right? Like, what are the brain structures that let him translate this information? But here's where the psychologist, I think, differs a little bit from the biologist, because this is the question that I come up with, which is like, how come we can't do that? You know, why is it that we don't have the kinds of cognitive skills to vocally imitate in any of the same kinds of ways? And I think this is the sort of psychologist's turn whenever they see animals doing interesting, cool things or lacking certain abilities, not doing the kinds of things that we do, is trying to turn to animals to try to figure out the psychologist's answer, which is that what can animal behavior actually tell us about us? What can we learn about ourselves about the fact that we can't do the things that the lyrebird can do, but that we can do lots of the things that the lyrebird can't do, such as be up here discussing animal behavior, or building buildings like this, or setting up PowerPoint slides, and so on. Why is it that we're so different? And the claim is that if we turn to non-human animals, we could actually learn something very important about ourselves. And I'm going to start by telling you two things I think that animal behavior can actually tell us about ourselves. You'll see this person later. This is my colleague, Brian Hare, who studies that last branch of primates other than humans, the ape branch. Here he is working with one of his chimpanzee subjects. But I'm going to make the claim that we can learn two separate things from studying animals. The first of the things that I think we can learn is a really important question, which is, what is unique to ourselves? It's obvious that we're a special species, right? No other species on the planet is doing what we're doing right now. But what is it about us that makes us so unique, what makes us so special? And again, we have to worry about this because we can look to other animals and realize a lot of things they do look very similar to what we do. You know, and I guess dog food companies kind of make fun of this. You know, maybe we're all bulldogs out there. But it raises this question of what parts of our mind are special to us? What is it that makes us special? Now, of course, we can hypothesize all kinds of things that might make us special. When we ask this question, we sort of turn to the kinds of things humans do, and we say, well, there are all these things out there that look pretty special. I mean, no other species is using language like we use it. No other species is using tools in the same way we use it. We have this sort of special culture where we can pass information on through generations. We develop art and beautiful kinds of theater and so on. And we can point to these kinds of things and say, you know, this is the stuff that kind of looks like it makes us special. Fair enough. But if we stopped there, we might miss something. Because to really answer this question, we actually have to ask whether non-human animals do any of the stuff like this. And when you actually turn to non-human animals, you see all these cases where they're doing things that look a lot like what we're doing. We see all kinds of cases of animal tool use. There's evidence that animals can transmit some information culturally. There's some evidence that even bees might have something like a language that's structured in some ways like our own. And there's even evidence that other animals create and design things seemingly for just the purpose of aesthetics. And that's the case of the guy up in that right corner, this bowerbird that I'll tell you about in a second. I'm going to focus on him for a second just to sort of hit you over the head with the fact that even though it looks like what we do is special, sometimes you can find rudiments of this stuff in the animal kingdom. And what the bowerbird does is the male bowerbird faces the same kind of problem as the lyrebird you saw before. He has to attract very finicky females to try to mate with them. He doesn't do it through an elaborate song. He does it through his artistic talent. And what bowerbirds do is they build what's known as a bower. It's kind of this nest-like structure, but it's not a nest. Nobody's going to live there. It really seems to be a showcase where the bowerbird can show off various artistic things he's done, such as collected these beautiful blue objects, such as the satin bowerbird. The satin bowerbird likes to design things using blue things, so he steals blue things from around his environment and arranges them in very particular ways. And if you were to go up and remove one of these blue feathers and move it to another spot, what you'd see is that the bowerbird would replace it in its same spot. So he seems to have his own aesthetic taste, and females pick which bowerbird to mate with based on that taste. I'll give you a sense of another bowerbird species. Here's another short David Attenborough video that sort of shows another Vogelkop bowerbird here.
And this is the work of the master builder among bowerbirds. I'm in the Vogelkop on the far western tip of New Guinea, and this is the bower of the Vogelkop bowerbird. And what an astonishment it is. Surely one of the wonders of the natural world. The bower has been completely roofed over, thatched with these stems of orchids. It's been built around the base of a sapling that has a stout pillar right in the middle, and it's got two smaller pillars on the side to support it. The whole of the treasury is 5 or 6 yards across, and what treasures it contains, or what variety of treasures it contains. On the far side, there are the black stems of tree ferns. Here is the lawn, neatly planted with moss, and on it, the shiny wing covers of beetles. There are orange fruit, there are these glowing orange dead leaves. These are the acorns of the oak trees, the tropical oaks, which are common around here. Behind me, there are black fruits, all of which has been bought specially by the bird.
So you get the sense that this isn't just some bird kind of putting stuff together. This is an artistic display area. It's got pillars, much like old Greek columns. It's got a planted lawn that the bird plants. It's got specific colors and specific spots. And we could ask the question, is this like human art? Should we pay as much for a bower as we do for a Jackson Pollock painting? And probably we wouldn't want to pay as much for the bower as a Jackson Pollock painting, but why? What's different about it? Point is, we can ask that question. We can think more about what makes us different, but we have to look at what animals are doing, try to figure out what they actually know to get there. If we just assume the animals don't do anything like us, we'd be remiss. We have to turn to them to really get the right answer to what makes us special. So that's sort of point number one we can learn from animals. The second point we can learn from animals is I think that turning to animals, in particular turning to other primates, gives us a powerful tool that I think physicists haven't even developed. Because turning to other animals, particularly other primates, can give us a time machine to look at what thinking and cognition might have been like back in the evolutionary day. So what do I mean by that? So you saw the sort of schematic version of our primate tree. Here's sort of the branch of the big animal tree that we're on. And one of the things we might wonder about is we said, well, we can study living adult humans, but what were we like over evolutionary time? What did humans look like back if we sort of scroll back through time over here, say 35 million years ago or 50 million years ago? As I said, we can't study those guys because they're dead, but we get some hints when we start seeing similarities and differences across the top of the branch. Say, for example, that we turn to some trait, some aspect of our thinking, and we see it's not just us that does it, but it's us and chimpanzees and rhesus monkeys and capuchin monkeys and lemurs. Let's say we find really robust similarity across the tree. Well, what we've done, I think, is to learn something about the old guy back here. We've kind of done a time machine thing because the parsimonious explanation isn't that that trait developed separately 5 different times. It's probably just pretty old. It's probably developed way back here. What this allows us is a powerful tool for looking at what human thinking looked like way back in very, very evolutionarily old ages. And allows us to ask questions like, what parts of what we do are specific to modern society? What parts of what we do are specific to the kinds of learning we have in modern society? And what parts are just built in, just super evolutionarily old? Figuring that out helps us figure out what we can change around through education and what we need to change around through other means. So that's a sort of second big question you can get at, sort of this question of what parts of the mind are evolutionarily old. So those are the two sort of big things we can get at turning to animals and particularly to non-human primates. Now I'm going to talk about specific ways that we've tried to look at how primates think about the world and have gained, I think, some important insights into the way humans might do it themselves. And the first domain I want to turn to ask this question is the domain about whether or not primates can think about number in the same way that we do. Now, here's a spot where we might think that we are unique to humans, right? Our species is probably the only species that does differential equations and complex calculus and so on. We know that that's probably true, but are there rudiments that we can see in other species? And what parts of mathematics do we bring to the table? Are children born with some propensity to do some aspects of numerical reasoning? Or is it all built up through training and teaching and culture? And so this is what we've been looking at a little bit, and what other researchers have been looking at by trying to see whether or not non-human animals, in this case the rhesus monkeys down in our field site, can actually count different numbers of objects. And so you might be thinking to yourself, how on earth can you ask this question? How can we ask monkeys what they know about number? Unlike what happens in 6th or 7th grade, we can't give the monkeys a math test because they don't talk. So we have to come up with some other creative kinds of means to get at what they're actually thinking about and what they know about in the world. And the way we do it, you saw a little bit in some of the pictures that I was showing you about Neha and Brian and others showing monkeys these sort of strange displays of different kinds of objects. What were they doing there? Well, it turns out we figured out an excellent way to ask monkeys about their intuitions about the world. And we use a technique that might be a little bit shocking, but we actually use magic. Not magic in the kind of, we fake it, hocus pocus. We actually use magical events to get at their knowledge of the world. So what on earth do I mean by this? Well, think about a magician that you might have seen recently. I always choose David Copperfield because I think he's my favorite musician. You will pay $50 a pop to go to the Civic Center to see David Copperfield do all these kinds of things, right? Why are we willing to pay to go see David Copperfield to do this stuff? Well, one of the things that David Copperfield is good at doing is he's very good at violating our intuitions about the way the world works. So it's cool to pay to see David Copperfield sort of split himself in half with a big saw because you know something about how human bodies work. You know human bodies don't sort of pop in half and come back together. That would be very weird for human bodies. You also know something about the way physical objects work. They don't float in air without a string attaching them somewhere. That looks really weird to us. And then two things happen. One is that we kind of enjoy watching these events, which is why we pay money to go see David Copperfield. But the second is that we get a little bit surprised by them. And that causes us to watch them for a really long time, as some of you guys are doing. I'm seeing the sort of faces where you're looking, trying to see, is there a string? Like, is that like, a false bottom? You're trying to figure out the trick. But you're only trying to figure out the trick because you know that human bodies don't work like that, that the physical world doesn't work like that. You have an expectation. You have knowledge in your head about something, and we can use magic to tap it. So that's the logic of doing monkey magic. What we're able to do with the monkeys is actually give them magical addition events, where 1 + 1 doesn't equal what you expect. And we're going to try to see whether or not the monkeys can do that really well. And I have up here a sort of version of what we do. I'll show you the non-magical event, and then I might need a volunteer from the audience to help me with some fake monkey magic. And remember, the monkeys aren't as savvy as you guys are. So this is not David Copperfield. It was free for you guys to get in, so don't expect a $50 show. But we can show the monkeys events where we actually show them something about how addition works. So we can show them adding different numbers of objects. So we can do one pair like this, and then we can sort of put down a screen and ask your expectations about if we put a second pair down in here. And then we can lift the screen and show you events that look like this, where 1 + 1 = 1. Or we could show you magical events. And so does anybody want to help me with a magical event? I'll grab you because I saw you first. And yeah. Oh, well, come on. I'll let you guys help next time. So I need to, what's your name? Anamika? Nice to meet you. So I'm going to whisper. You have to talk amongst yourself. So I whisper to Anamika how the magic works. And so I'm going to show you how the magic works. So we're going to add 1. So that when you lift it, it looks like it's missing. Does that make sense? You want to try it? Mm-hmm. All right. So we're going to add 1 to the stage. All right. She's adding 1. And then we're going to put the screen down. You're going to add a second one. You're going to add a second one. Make sure it goes on there. Very good. And ready for the big dun, 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 dun. 1 + 1 = 1. Thank you. As I said, the monkey magic is not as magical. Some of you over there are seeing the trick, but But to the monkeys, this is pretty shocking because they're watching 1 go in. They're seeing me add a second one really quickly, and then I lift it, and there's only 1 there. So the question is, do the monkeys notice this? Are they shocked by it? And this is just what we're able to do. Here's how it looks when we run it in our field site. Sorry to keep moving the lights around. But what we have is we have one person who's doing the kind of thing that we were just doing up here, where they're the magician. They're sort of putting objects into these boxes and running the magic. Importantly, we have a camera person who's just filming what happens with the monkeys. Do they get surprised? Do they look for a really long time? And all importantly, we have the monkey who's sitting there who's watching the event. And we're videotaping his reaction, and we come back to the lab later, and we just measure as a measure of surprise, how long he watches it. Is he shocked enough to watch for a long time? And they just see events like the one you saw. So we'd add one eggplant to a box, hide it up, and then add a second eggplant, and we show either expected events where 1 + 1 = 2, or unexpected events in which 1 + 1 = 1. And the expectation is when we show the monkeys expected events, this should be really boring. We should get videotapes that look like this. The monkeys are yawning. They're just not into this at all. Versus cases where 1 + 1 = 1. And here we expect videotapes that look like this, where the monkeys are shocked, marveled in awe. They're happy to pay $50 to see this. But what we've been able to do with this sort of technique is to actually show that monkeys know something about very simple arithmetic. So in the top case here, where 1 eggplant at the top + 1 eggplant = 2, we see that on average the monkeys look for about 1 second. And it's a reasonable look, but they're not that shocked. What happens in the case as in B, where 1 + 1 = only 1? Well, we find 3 to 4 times that amount of looking. So the monkeys stare for 3 to 4 seconds. Again, they're not so shocked that this is blowing them away, but we see a difference suggesting that they understand that something was wrong from the arithmetic that they know in that case. Same thing when you have 1 + 1 = too big a number, like 3. Again, we see these 3 to 4 seconds of looking. And so I'll show you a quick video of what this looks like. And I apologize, the quality of this video is not great, but it'll give you some idea of what it looks like to run these studies down at the field site.
Using a portable magic stage, Laurie and Sue are now investigating whether the monkeys can also do basic addition. The experiment works like this. A lime is placed on the stage and a barrier put down to block the view. After a brief pause, another lime is added. 1 + 1 = 2. No magic there. The monkey quickly loses interest. It's videotaped to measure later how long the monkey looked. Now here's another show. It's identical to the first except for the surprise ending.
Watch. Ready?
1 + 1 = 1.
Now.
The monkey stares for a long time, many seconds more than before. Sue believes this means the monkey was surprised, that it must have known something was wrong. Such looking time experiments, as they're called, were actually developed to figure out what's going on inside the minds of human babies. When shown non-magical events like this one, 3-month-old babies get bored rapidly. But show them an impossible or magical event like this. The infants stare and stare. Their fascination with magical events suggests they know the world doesn't work this way.
So the point is we can actually use magic in some cases to get at what monkeys know. And when we did this in the case of number, what we found is that monkeys seem to have some of the rudiments that we do. They do the kinds of basic arithmetic you see early on in human development. And it turns out with future work, we found that monkeys can exactly compute arithmetic up to about 4. And then they do pretty good even with big numbers if you give them big ratios. So they'd know something like 5 + 5 is more likely to be 10 than 5. They'd sort of be surprised at 5, but maybe not at 8 or so on. So we're getting to the rudiments of these basic arithmetic abilities in the monkeys. But one of the things we saw when we were running these studies ended up launching a new line of investigation. And this is relevant to tell you guys about because sometimes the progress in science, you think it's the way you read about in textbooks where you have a hypothesis, you think about the question, and it's kind of the way you sort of see the scientific method in a book. The way the scientific method really works in the field is that you have some observation, some unexpected thing happens, and this gets you to start thinking about, wait a minute, like what was going on there? It generates new questions, and then you can ask these new questions. And so this is what launched some of the work that we started trying to see what monkeys knew about other minds. And it happened in an unfortunate incident, somewhat like this, where we're testing the monkeys. We've got our little fruits that the monkeys might watch. We're sort of lifting the screen. And all the time when we end, we do the thing that you see me doing up there, which is we don't want to cue the monkeys, so we just slightly turn to the side so we're no longer looking. Of course, that also means we don't know what's happening with our box and if potentially a monkey who wanted to steal the fruit was about to do that. So this is what one of the videos looked like.
Board. Hey, 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 you.
And that's bad camera people trying to prevent a monkey from running off with our eggplants, which unfortunately happened. So we had to go home early that day because we didn't have any more fruits to do our magic, and that was very sad. But it was exciting because what we realized was that something was going on, because the monkeys seemed, like in these cases where they did this, to be smart about deceiving us only when we didn't know what was going on, only when we weren't looking. So we asked the question, well, maybe the monkeys actually know not just something about arithmetic, not just something about the way numbers work and physical things work. Maybe they know something about how other minds work. Maybe they're tracking something about what's going on inside our heads. And it turns out that if you think about how hard this problem is, it's actually trickier than you might think. So it's tricky in part because we seem to do it very easily. We forget how difficult it is. So if you saw this image in this world of this girl with her eyes pointed at the cookies, you would immediately think certain things about what's going on inside her head. So what are some of the things you might think when you see this picture? She wants the cookies, yeah? She wants to steal the cookies, which means something else. Is that it's not just she wants the cookies, but she knows maybe her parents don't want her to take the cookies, and she's trying to do something when her parents don't know that she has the cookies. Look how complicated this is. What you have just done by thinking about this is thinking about not something that's in the world and behavior. You're making hypotheses about what's going on inside her head, not just her head, the head of somebody that's not even in the frame, some mother who's somewhere maybe monitoring this. It turns out that this is computationally an incredibly tricky process. How do we take just what's in the world and develop theories about intentions and desires and beliefs and knowledge? We never have direct access to that. We probably do it in part because we're helped by language. We have words like know and intend and believe and desire. That helps us probably figure this stuff out. But what about a non-human animal that lacks language, that doesn't have those words? Could they ever think about what's going on inside somebody's head? Do they know what it means for somebody to see something? Can they sort of fill in that box up there? Well, a lot of researchers have tried to look at this, and I'll start with some work in chimpanzees by my colleague Brian Hare, in part because he's done some of the pioneering work in this area and also some of the loveliest. Brian works with a set of apes. He works both with chimpanzees and bonobos who are on the ape branch. He works with them out in a sanctuary in Africa. And this is just a short public service announcement, which is that even though the monkeys and the apes that you see in this setup are cute, you should never have one as a pet. And the reason you should never have one as a pet is sort of shown by where Brian actually does his work. This is a sanctuary in Africa, and it's home mostly to very young chimpanzees. And the reason is that these are all orphaned chimpanzees, orphaned because their parents were killed in order to capture them for the pet trade. The ones that Brian has at the sanctuary are ones that were caught at the airport, but they were all being moved over to the States to be pets. And so this is sad. These are these orphans. Parents are getting killed. Do not have a chimpanzee as a pet. It's dangerous, and it's kind of ethically a little bit sketchy. But this is the spot where Brian actually works. It's this lovely sanctuary in Africa. The apes get to free range around, and when they're interested in coming in to do testing, they can come into an enclosure inside and sort of play with Brian for some treats. So typically they live outside. They come into these enclosures. Here are some videos about what it looks like when the chimps are in the enclosure. And Brian's going to be running a study here to ask whether the chimpanzees actually know something about what he can see. And so I'll give you, this is going to be a video in a sec, but I just want to set it up for a bit. Here's a cam of Brian. He's sort of sitting there on this side. The top left is what's happening on the left of where Brian is, and that's what's happening on the right. And Brian's setting up a study where there's this delicious juice that Yahaga, this chimpanzee, wants, but he's trying to convince her that he's a scary, dominant competitor and that she can't take it. So it's kind of like with the kid with the cookies and the mom. So Brian's being the mom, Brian's saying, no, you're not allowed to take the juice right now. And you can sort of see what happens here, where Yahaga, the chimpanzee, tries to go to the side and get that little bottle of juice, and Brian's like, no, it's like the mom, you can't take the cookies. And so Yahaga runs to the other side. Maybe he won't see me on the other side, but Brian's like, no, I'm going to follow you there too, and she runs to the other side. And so this is like what's fun about working with primates, and Yahaga does funny things like roll on the ground. But the point is that Brian gets good about teaching her. He's going to be like the mom. He doesn't want her to take the juice. Question is, are the chimpanzees savvy, like that little girl, about taking the cookies when nobody's watching? And what you can see is it's exactly the same setup, except this time, Brian's put up this big opaque barrier. So now it's not clear anymore, it's colored, which means that if she were to try to sneak to that side to steal the juice, Brian might not be able to see her. And so Brian, because this is his experiment, he's sort of freeze framing and letting her do her thing. You can see she kind of thinks about it. Well, it looks like she's thinking about it for a second, kind of goes off to the side. And for a while, she sort of is thinking about it so much that she goes back to the outside. She's no longer in the closure. Brian's freeze framing. And this is where, if Brian was savvy with these videos, he'd put in some sort of Mission Impossible music, or like spy music, because what happens is Yahaga very quietly sneaks back, and she's very excited about this because she's figured out what to do. She's going to sneak to the side that Brian has and actually get the juice. So on the first trial, they're very smart about this. They use barriers to block what people can see. Do they also understand not just seeing, but things like intentions? And that's something else that Brian was up to with a different chimpanzee here. Brian's actually doing a study where he's just normally doing what he would do, which is to sort of feed Yahaga treats when she comes inside to play these games. But all of a sudden, he stops doing that. So the outcome is going to be bad in all these cases. He's not going to give her treats anymore, either because he has a good intention, but he just can't act on it. He's trying to give her food, but he's becoming clumsy. He keeps dropping things. And that's going to be the first case, versus a case where he has a bad intention. So what's going on in his head is bad. He's going to be trying to tease her. And all of you know that, who have kids, know that these kids pick up on this easy. If you have really younger siblings, you know younger siblings are good at figuring out whether your intentions are good or bad. What about chimpanzees? So here's a case where he has good intentions, good things in his head, but he's just become clumsy. And this video looks like it's getting stuck a bit, but you can see what happens, which is that Yahaga just hangs out here. She's sort of waiting for him to overcome his clumsiness. He's like, oops, sorry, sorry. But his intentions are good, so she doesn't react badly to this. What happens in the case where his intentions are bad? And so this is the case of teasing. So it looks the same. She's still not going to get the food, but haha, he teases her, and she says no. Very, very different reaction. She's out of there. She's going back to hang out with her crew. She doesn't want to play the game anymore, right? This is relevant because the behavior is the same. She's not getting food in both cases, but the chimps are picking up on what's going on inside someone's head. What about the case of more distantly related primates, such as our monkeys down at the field site? Well, we wanted to do the same kind of thing with our monkeys, and as you saw from the looking time studies that I was showing you before, the monkeys seemed pretty good at stealing from us when we weren't looking. So we said, well, let's just set up an experiment on this. So we brought down 2 other undergrads who go down to the field site. In this case, they're going to be like Brian. They're going to be the moms who are competing against these monkeys for food. They each stand in front of a little platform with a grape, and the question is, which one do the monkeys actually steal? And you probably guessed, since the monkeys were good at this before, that the monkeys might be good at this one. Here's just a short video so you can see
Who isn't
like.
looking?
So we put the platform down, we're all looking, and then one person turns away, and you can see the monkeys run up and take the food. So turns out the monkeys are really savvy at this. I'll show you some graphs. Basically, I'm just going to plot. The black bars are how many monkeys get it right. And what you can see, when the person's head is just turned, not even their whole back turned, but just their head turned, most of the monkeys get it right. They even get it right if you're just looking away. So you just turn away briefly, they get it right. And even when you give these kind of weird, novel barriers, they figure it out. They seem to be thinking about what's going on inside someone's head, which is really, really cool. We also were able to show with another set of undergrads, this is Aaron, who's down there at the field site, that the monkeys know about something about what it means to hear. And so this time, we're going to be putting food not on these flat platforms, but inside these weird boxes. The boxes are transparent, so the monkeys can see what's in them. But what's relevant is that they're covered in these golden jingle bells. And so as Aaron's putting the food in one of these boxes, the monkeys can actually hear that this box is making a lot of noise. As he's putting food in, it's making a lot of noise. Probably not a good box to steal, because the person might hear you. The second box looks exactly the same. Visually, it's identical, but we've taken the balls outside of the little jingle bells. So even though it looks the same, the monkeys can hear when Aaron's putting food in there that this box is totally quiet. And so now the boxes are loaded, Aaron steps back, and he just looks away for a little bit. And the question is, what do we think the monkeys are going to do? Which one are they going to steal from? The quiet one, right? And this is just what we find. When you plot how many monkeys steal from things, they actually steal from the silent one. So on the first trial, they get it, these totally novel bells and all this stuff. They steal from the one that you can't hear. But we gave them one more hard problem. So now everything was the same, except this time, when Aaron steps back, he can already see what's going on. So what he can hear doesn't matter, because he can already see. What do you think the monkeys are going to do here? Are they going to do the same thing or something different? Something different. Very good. And that's actually what we find. Here, the monkeys don't show that same preference. If anything, they kind of go to the noisy one. And that's because probably all things being equal, the monkeys like to make a bit of a ruckus. They like being a little bit noisy over time. But the point is that it means that the monkeys are thinking about the very thoughts that are going on inside our head. They know something about what it means to see and hear. They actually use that to deceive us, so they don't use this always for the nicest purposes. But they seem to get this thing, which is computationally really tricky. They can think about what we're thinking. So that was test case number 2, and I'm going to end with test case number 3, which is some recent work that we've been up to trying to see whether the monkeys know something about what it means to use money. And we started this work in like a few years ago, right around the time of the financial collapse, where I was in my lab talking to my students using humans as this sort of paragon of how smart we are, or sort of the benchmark against which we're testing our monkeys. And then I would go home and watch the news and see humans doing incredibly stupid things with their finances, watching traders make errors, watching banks do these silly things. I said, well, hang on, there's a little bit of a disconnect here. These bankers and investors and folks have lots of experience, but they still seem to be doing things that might not be so smart. And we said, well, maybe it's just like number or this idea of how we reason about minds. Maybe there's something built in to the kind of errors that we make with money. And so this launched the kind of work that we've been up to with our capuchin monkeys here at Yale. We've been trying to see if we can actually teach the monkeys to use something like money and then see what they do with it. Do they do the smart things that humans do, and do they make the same kinds of errors? Now, we couldn't give the capuchin monkeys $5 bills because they might tear those up, so we had to have something a little bit more durable. But we made our own aluminum capuchin coins. We sort of made our own sort of capuchin money. It's kind of boring. It didn't have the sort of flashy look of some countries' money. But they kind of got it. We sort of introduced these coins to them, and then we allowed them to trade them with people for pieces of food. And our monkeys are very curious. As soon as you put these things in, they're like, what are these things? They immediately pick them up, and if there's a person waiting with food, they kind of get very quickly, oh, I can do this swap. As soon as they pick this up, basically we had a monkey market that we could use to ask these kinds of questions. So here's Mayday, one of our monkeys. She has her little monkey money. At first we used metal washers, and then we sort of upgraded to this new currency. But she quickly gets so she can hand over these things with humans. And here's another kind of slightly more French New Wave version video of this. Here's Felix, who's one of our, or here's Mayday again. She hands over the token and gets her food. So she gets good at this. Here's Felix, who's our alpha male. He's a big guy. Hands over the token, gets food. All right, so they get very, very good at this. And the question is, does this just look like using a currency? Or are they really paying attention to the kinds of things that would matter for humans using a currency? For example, do they pay attention to how much food they get for their dollar, as it were? Do they pay attention to price and these sorts of things? So we launched into a whole series of studies to show this, and I won't have time to go through them all, but I'll just give you a flavor of what we found, suggesting that the monkeys get this market. It sort of works in the same way as human markets do. Now, rather than trade with one experimenter, the monkeys are going to get a choice between two different experimenters. So they get to kind of leave their enclosure, they come into the spot where they can trade with the humans, and then they actually get a choice. So the monkeys can trade with Kirk, who seems like he's offering one grape, sort of in this dish. That's what the monkeys think they're going to get. Or they could trade with Justin, who has 2 grapes. And the question is, if you were a savvy capuchin shopper, would you shop with Kirk in the red or Justin in the purple? You shop with Justin. All right, let's see what the monkeys do. So here's a video. This is kind of a monkey eye view. Here's Honey, one of our monkeys. She's sort of waiting for the market to open. You can see we only get chest level, the monkey eye view. But the market opens, and she checks out her choice, 1 grape or 2 grapes. Who's she going to shop with? She shops with Justin. So very savvy monkey consumer. Most of our monkeys shopped with Justin at about rates of 70 to 80%. And this was not the only smart thing they did. This is paying attention to who gives you overall more food. The monkeys cared about price. So if all of a sudden Justin dropped his price, and the way we do that with the monkeys is the price is always 1 token, but you can get more food. It's kind of like when you go and get big laundry detergent that you get the extra for free. That's actually cheaper laundry detergent. So we did this where Justin or Kirk would kind of decrease or increase their prices. The monkeys responded rationally to all these things. In other words, they correctly shopped at the guys who gave them better deals. So it seemed like the monkeys, in all these cases, were doing smart things with monkey. Monkey and money sounds way too similar, but they do smart things with money. The question is whether they do some of the not so smart things that humans do. And just to see a flavor of some of these not so smart things, I'll have you guys play in a money experiment that's known to elicit some people's biases. So imagine that Science Saturdays gets an enormous endowment from some rich alum, and I'm able to offer you guys not just really cool science for free, but $1,000 for coming to Science Saturdays. I bet every seat here would be full if we did this, but sadly we can't. But imagine you just get $1,000, right? So this is the game we're going to play, and really play along. Like if you had $1,000 right now, what would you do with it? What would you buy? But it's not just $1,000. You have a chance to earn more money. You either get a choice to take a risk. So we're going to gamble. I'm going to flip a coin, and if it comes up heads, you're going to get $1,000 more. Or if it comes up tails, you get nothing. So that's your first choice. Or you could just play it safe. And you could just take an extra $500 from Science Saturday for sure. You don't have to flip a coin. And so again, audience participation, who goes with the take a risk one? Good. Who goes with the play it safe? A lot more people. And that's actually what you find when you test people with this setup. Most of the people, around 70%, choose to play it safe. That's not irrational. That just shows we're a little risk averse. What's irrational is what happens when you give people a slightly different version of the same scenario. So now imagine that we gave you $2,000 for Science Saturday. This seems even better, but it turns out it's actually kind of bad, because the choice you have to make is how to lose some of the $2,000 you just got. You have to give some of it back. You could either give it back in a gamble, where I'm going to flip a coin, and if it comes up heads, that's very bad. You have to give me $1,000. Or you could keep it if you are lucky and it comes up tails. Or you could choose to play it safe, where you don't have to take the gamble. You just give me $500 back with certainty. And those of you who are good at math might be figuring out, well, hang on, that is exactly the same as what happened there. It's either $1,500 for sure, or $1,000 or $2,000 if you go risky. And some of you are smiling, which I think means that you're getting the intuition, which is that when you see the problem like this, what happens is most people don't want to play it safe anymore. In this case, what happens is most people want to be risky. They want the chance that they're not going to lose any money and can keep the whole thing. This is totally irrational, because what it means is you have a different risk preference just based on what you started with, which doesn't actually matter for what you get in the end. It's an example of all the kinds of biases that we see that plague the market right now. And what we wanted to do was to see whether we could see the same kinds of biases in the monkeys. Just to sort of put it in perspective, to give you a sense of what these biases are, what you just showed in that scenario, if you felt that intuition, were two biases that economists find very funny. The first bias is what economists sometimes refer to as reference points. Economists sometimes think that when you're making choices about your money, what you should think about is only absolutes. How much wealth overall you have, or how much happiness you can get overall. But that's just not how people think. If you were to leave here from Science Saturdays and walk out to your car and saw that you had a parking ticket from the New Haven parking ticket office, you probably wouldn't look at that parking ticket and calculate what's in your bank account right now minus the parking ticket. You wouldn't think in terms of absolutes. You'd probably say some expletive, maybe cover your children's ears, and say, $20, like I was just up $20 before and now I'm down. And this is the power of reference points. We don't think in terms of absolutes. We think in terms of the status quo, a certain reference point, as it were, and we see changes relative to that. So when you guys started with $1,000, getting a safe bet seemed good. When you start with $2,000 and you're going into the red, you behave very differently. And the going into the red behavior is the second bias that economists talk about. It's a bias known as loss aversion. We really don't like going into the red. We really don't like losses. And sometimes that causes us to do strange things to avoid them, like taking on more risk than we might normally like. Turns out we gamble more when we're dealing with losses, just as you guys did in that scenario. So how do we translate this into asking the same questions for the monkeys? What we wanted to do is give the monkeys exactly the same survey as you guys just took before. But how do we do that? Well, what we reasoned is that the monkeys, we could actually sort of give the monkeys 1,000 or give the monkeys 2,000 by varying what the different experimenters actually started with. So here's starting with a low amount, and both experimenters are going to give you more. It's like the first scenario. Vlad, who's on the left here, he is actually the safe guy. So every time the monkey trades with him, even though he starts with 1, he actually gives 2. So this is like getting $500 with certainty. You're going to get more. It's a small amount, but you know you're going to get it, because Vlad does the same thing every time. What about Wesley? Well, Wesley's very risky. Sometimes you just get 1, so sometimes you get no gain, but sometimes you get a big gain and you get 3. So this is exactly, if you're paying attention, it's exactly the same scenario we gave to you guys. And this is the monkey's choice. Do they want to get a safe gain with Vlad all the time, or do they want to take a risk? And what you guys did was you wanted to play it safe. What do we think the monkeys did? Well, exactly what you guys did. They want to actually play it safe. In this case, they trade more with Vlad. But what happens when the monkeys are getting less than they expect? And so this is how we do the less than they expect. Both experimenters are showing the monkeys more food than they're going to get. They actually take some of the food away. And I can tell you none of our experimenters like taking the food away from the monkeys. They feel very bad about it. But the monkeys respond to these losses very sharply. And so here's when the monkeys get a safe loss from Alex on the left. The monkeys think they're going to get 3, but Alex always takes 1 away. To give the monkeys, again, a good bet. He's giving them 2, but every single time he takes 1 away. What about Venkat? He's a risky loss. Sometimes he doesn't take any away, but sometimes he takes a lot away to give the monkey only 1. So you should see this as very familiar. It's exactly the same choice between 2 for sure or a risky 1 or 3 that the monkeys got before. But now the monkeys are losing. What you guys did here was you became more risky. Question is, what did the monkeys do? Exactly the same thing as you do. Here, they actually shop more at venkat because sometimes they have a chance not to get any loss at all. It's exactly the same bias we see in the monkeys, seems to play out in human markets, in the housing crisis, on the golf course, and even in the case of stocks where people don't invest enough in stocks that sometimes dip down. All these biases we see in real markets, we see in the monkeys as well. And what this has allowed us to learn is that something about the way we deal with money seems to be shared across a bunch of species. Maybe it's not just that we're all bad and have had difficult experiences with money where we don't get it. Maybe something about these strategies might be built in interestingly from the start. And so that's the work that we've been up to with the monkey money. And now I kind of want to wrap up quickly about what all this stuff means. Sort of what all this stuff means for the fact that the monkeys use money, for the fact that they can count a little bit, for the fact that they reason about other minds. Well, I think what this means is that we've learned something about what's uniquely human. It seems like none of these things are specific just to us. The second thing we've learned is something about our evolutionary time machine. What we've been able to see is it's not just humans that show these smart capacities or these biases. We see some of these in rhesus monkeys, as in the case of the work on minds and in the work on number. We see some of this in the capuchin monkeys, as in the case on number. And I think what this has done is allowed us to kind of figure out something about the guy that was back here. Seems like this guy might have known something perhaps about number, something about the strategies that we use when we're dealing with money. Seems like all of these things are much more old than we might have thought before. And if you want, in the discussion, we could talk about, well, what does that mean when we're dealing with biases or some of these other capacities? But it means that we've answered this interesting question about what comes to us from the start, some of the things we might not have expected initially. And so that's where we kind of wanted to stop. But I wanted to sort of end with a little bit of an advertisement, because if you're like me, as I sat in the auditorium and heard this stuff and saw the beautiful palm trees, I'm hoping that I'm getting you excited about these kinds of questions. And it might feel a little bit frustrating, especially for some of you who are younger. Maybe someday you'll come to Yale and work in my lab and head off to these fabulous places, but you might have a few years in there before you can actually do this stuff. So what can you do if you really want to study animals, but you don't have access to monkeys or lemurs or apes like these guys here? Well, what I want to submit to you is that you guys probably have the opportunity to use some of these techniques yourself. Well, what do I mean by this? Well, you don't maybe have access to cute monkeys in tropical places, but I bet at least some of you have access to a population that might be interesting to study. Perhaps guys like this, or guys like cats or gerbils or this sort of thing. What I've shown you is a couple techniques that, yes, they work on monkeys, but there's no reason that you can't use the same techniques to try to get at what your own pets understand about the world. Well, how would you do this? Well, you just do the same kinds of science with your pets that we do here. You can see, for example, if your dog understands something about number. Well, how do you do that? Well, you have to invest the $4 or so in this little cardboard thing. If some of you want to take, or I can let one person take this one home with the pairs, but you can just do something like this with your own dogs out there. Instead of a lemur, you'd have a dog. You probably don't want to use lemons or fruit, maybe some toy that the doggies like. But you can do the same kind of magical event that I just showed. I will reveal my secret of how it works for those of you who didn't already figure it out. But what you can just do is do the same thing we do. You videotape your dogs or just time how long they look. Do your dogs actually understand arithmetic? Can they be better than the monkeys? You have the tools to actually ask this question. You can try to see whether they show the same pattern that we see in monkeys. You can also do the same thing of trying to figure out if your dogs or cats actually understand something about the way the minds work. What we saw is an incredibly simple technique where if you have something that your dogs might not want you to take, you could sort of set it up just like this. Instead of a monkey, you could use a dog, try to see if the dogs actually know something about which ones you know about or which ones you don't know about. The cool thing is that all the techniques I've shown you aren't things like particle accelerators or complicated tools. They're just a bunch of cardboard and little pieces of food. You guys can start being scientists today if you have pets at home, and maybe you'll learn very, very new things about the way the animal mind works. So I hope I've convinced you that studying the way humans work can be achieved through this evolutionary approach, sort of trying to look as far across the evolutionary tree as we can. And with that, I will sort of end with two things. One is to thank my students who can't be here. You've seen many of them in the talk, but I always tell people that I'm this monkey over here, and I get to sort of sit there, and all the science kind of happens with the hard work of all my students who you've seen in this talk. But I also wanted to end with an advertisement. If you're into this stuff, and you're around the area, you have this wonderful resource right here at Yale where we actually have the capacity to study primate cognition here on campus. And we're also affiliated with all these cool, fun, tropical places where you can study primates too. And that's it, and I can pause for any questions folks have.